Around the world, millions of users hit stake-level firewalls every day. To get past them, they rely on two main options: academic circumvention tools and high-bandwidth commercial VPNs. Systems designed by researchers, like Tor or Snowflake, are highly effective at hiding internet traffic. But because they route data through networks of volunteers, they cannot provide the bandwidth necessary for daily use. Users experience speeds that make streaming or heavy browsing impossible. Commercial VPNs solve the bandwidth problem by owning massive server infrastructure. However, they rely on standard protocols like WireGuard or OpenVPN. State-run Deep Packet Inspection, or DPI, easily fingerprints these standard protocols and drops the connection. This creates a persistent engineering gap. Citizens living inside censored networks are forced to choose between reliable access to text and news or usable speeds that quickly get blocked. To solve this, a circumvention tool must combine the obfuscation of an academic protocol with the sustainable infrastructure of a commercial network. Jeff is a production-scale circumvention system that does exactly this. It operates inside the world's most hostile network environments, passing roughly 600 terabytes of user traffic every month. During major state internet shutdowns, that scale translates to supporting up to 500,000 daily active users. In places like Iran, maintaining that connectivity dictates whether citizens can organize or access outside information. Jeff sustains this operation without inventing new cryptography. Instead, it abandons standard VPN architecture. It relies on aggressive network arbitrage and a localized economic model to stay online. Bypassing state firewalls is ultimately an infrastructural and behavioral problem, requiring a system designed specifically around the censor's economic and physical limitations. When a user turns on a standard VPN, it attempts to shake hands with a specific IP address. The censor identifies that IP as a VPN server and severs the connection immediately. Jeff avoids direct connection entirely. The client first communicates with a central server called the broker. It does this using domain fronting, packaging the handshake request inside HTTPS traffic headed to a highly reputable content delivery network. The censor cannot block the CDN without causing massive collateral damage to normal internet traffic. Once inside, the broker authenticates the user to confirm their subscription tier. It uses blind signatures, a cryptographic method that verifies a user's token without recording their identity or tying the connection to a specific account. With the user verified, the broker issues a route descriptor. This is a dynamic set of instructions detailing exactly which external servers to contact and which nested protocols the client should use to establish the final connection. By decoupling the authentication process from the actual delivery of payload data, the system prevents the censor from killing the network through a simple blacklist of entry IP addresses. State censors continually update their techniques. They have largely moved past inspecting individual connections and now utilize ISP-level behavioral analysis. A firewall will monitor the overall shape of a user's traffic and block them if their total data usage resembles a VPN. To deliver the actual payload under this scrutiny, GEF uses a custom implementation of OBFS4, a protocol originally designed for Tor. By writing it in Rust, the developers optimized it for high-performance production environments. This custom protocol applies heavy cryptographic padding. It injects randomized dummy bytes into the data stream, constantly altering both the size of the packets and the exact timing of their transmission. Simply encrypting the data payload is no longer enough to evade detection. To maintain a connection, the system must continually disguise the meta behavior of the traffic itself. Even if traffic evades DPI, it hits a physical barrier. The state firewall acts as an intentional choke point, severely restricting the overall bandwidth available for international internet traffic. Censored ISPs further degrade performance through poor BGP routing. A data packet traveling from an Asian city to a neighboring country might be routed across the Pacific Ocean to the United States and back, introducing massive latency. GEF solves this by deploying untrusted relay nodes called bridges strictly outside the firewall. These bridges are hosted on commercial cloud providers that have already negotiated preferential peering agreements with the censored ISPs. The client software does not rely on a single path. It employs a happy eyeballs race algorithm, simultaneously testing multiple bridges at once to identify which undocumented route currently offers the fastest speeds. Live telemetry proves how critical this is. For a user on China Mobile, Autonomous System 9808, the most efficient path naturally routes through Linode servers located in Japan. But for a user on China Telecom, Autonomous System 4134, that same Linode path is congested. Instead, their optimal connection routes through AWS Lightsail infrastructure. Delivering usable speeds under censorship is primarily a physical infrastructure problem. It requires continuous, automated arbitrage of undocumented telecom peering agreements. The state's final technical countermeasure is bridge enumeration. The censor spins up automated clients to pull the IP addresses of every available bridge and then immediately blacklists them. The free tier of Jeff is vulnerable to this. The defense relies entirely on using low-cost commodity cloud computing. The moment an IP address is blocked, an automated system drops the dead server and spins up a new instance in a different region. To enumerate the premium tier bridges, the state faces an economic barrier. A user must possess a paid account to receive premium server IPs. Therefore, the censor must purchase a commercial subscription to find the bridge. This creates an unwinnable mathematical reality. The financial cost incurred by the censor to discover and block a single premium node directly provides GEF with the capital to provision multiple replacement servers. This system is sustained entirely by a gray market payment pipeline. Local resellers accept standard domestic payment apps like Alipay, convert the funds into cryptocurrency, and forward it to GEF. By integrating a commercial business model directly into the architecture, GEF turns a lethal technical attack into a financial loss for the state. It builds an asymmetrical defense mechanism that censorship budgets cannot defeat. Maintaining this architecture requires treating the network as an active battlefield. State actors are continuously developing and deploying intelligent firewall rules to isolate VPN traffic. Jeff monitors these deployments in real time. By observing sudden drops in regional traffic data, the system detects exactly when and where a new block occurs, triggering the automated systems to rotate IP addresses. But the most crucial intelligence comes from the inside. Power users living within the censored regions volunteer to run sandboxed testing environments on their local machines. In exchange for a free premium subscription, these users provide developers with secure SSH access to their virtual machines. This creates an invaluable observation post, allowing developers to probe the firewall directly from inside the target network. Defeating the Great Firewall is not accomplished through a single static algorithm. It is achieved by engineering an agile, self-sustaining loop, combining real-time network arbitrage, academic cryptography, and hard economic leverage to outpace the censor every single day.